All right, guys. So go ahead and open your notes packet. And we were on this example with Sally and Mike chatting about their scores. So I want you guys to try to do this one with your neighbor, with, you know, some help from a friend here. But see if you remember how to do this on your calculator. But go ahead and give this one right here a try. Okay.
Do we need to know H on the last question? Okay.
You need to know H. Oh, I think that's what this, about 21% of test takers. Sorry, I was like, H. I understand now. Literally part H.
Was the percentile?
I have started on a test. It's the stuff we were doing last time.
You're trying to find like
The calculator, I don't know if you remember looking at that. Give me just a second.
So you have to use this C-square.
Oh, but where is this? You don't have it. Yes, and a little stuff.
Oh,
I think we slightly.
you're given
I don't remember. Like, because we only have the percent, not like her score or her use or the here.
Can't make you do this one on your own. Okay, guys. Let me help. I'm making you do one on your own that you haven't done before. So. Hey, Ryan, you get your mask up. Okay. Sorry, guys. You hadn't done one like this. My mistake. Okay, so on this one, all we know is that Sally scored in the 75th percentile. So we have to kind of work in reverse from what you were doing before. So I'm still going to make a picture, just because it's a good habit to get into. So we were talking about the ACT, which remember was centered at 21. So guys, what percentile does that score of 21 line up with? 50th, okay? So if she's the 75th percentile, she'd be somewhere over here, right? We okay with that? All right, what you were using before on your calculator was normal CDF, like the normal cumulative density function. We're trying to work in reverse from that, okay? So you're going to use what's called inverse norm, sort of undoing the normal. So I'm going to write inverse norm, and then I'll pull up my calculator here for us. All right, so you get there again by going into that distribution menu. So second vars takes you into the distribution, and then we want to pick inverse norm, which is the third one down. Okay, so the area, that's talking about which part of the curve has been shaded in. We want to talk about up to the 75th percentile, so we're going to say an area of 0.75. So if it was the 99th percentile, you'd put in 0.99, okay? Now, we don't have anything standardized here, so we're going to go with our mu and sigma that we know about the ACT. So I'm going to plug in 21 and, oops, maybe 6. Those were given to you. I know it's been like a week since we worked on this, so.
For tail, should I just say center?
Let me see what yours says. You guys have tail choices?
Yeah.
So guys, you'll want to do the left tail for this one, and that goes back to like what we were talking about with the area. We want up to the 0.75, so the left side of that. Mine obviously doesn't have the left, center, or right. But you should get 25. Yes. Yep, you could. Okay, questions there, guys. What this is telling us, this is working backwards and telling us what her score was on the ACT. So the 75th percentile was a score of 25. And yes, Io, you're right. You could just use the Z-score formula, do it by hand. If you missed some algebra, you could certainly go back and do it that way. That's totally fine, okay? Anybody calculator troubles? Anybody going, ugh, that's not what's happening on my calculator? Anybody?
For the tail, if we don't know which option to pick, if we pick the wrong one, will it change the number?
Try putting right in. What does it give you? Does it give
You
you?
put center and it goes
Like the
different.
center, and it was like the
Oh, that's weird. So I would do left because if you think about this picture, do you see how it's like left of that 0.75? That's what you're thinking about.
Okay.
Does that make sense?
Yeah.
Okay. All right. So on mine, I did 0.75. My mu was 21. My sigma was 6. Raise your hand if you didn't have the left, right, center choice. Okay. Interesting. Those were new calculators. No, I don't know why it's on there. That hasn't come up before. So, all right. Questions on that one? So we would just want to write out, you know, Sally scored. Let's 25 on her ACT. Okay. Okay, now I'm going to have you guys try one, now that we know about inverse norm. So Go ahead and try the one here about the weights of labs. Yeah, go ahead. You know, they give you the mean and standard deviation. Definitely make a picture. But let's talk for a second about what it's asking you for. It says, what's the IQR? So what percentiles are associated with the IQR? So it's the middle 50, but from what percentile to what percentile? Yeah, so you're going to have to figure out the score for the 25th percentile and the 75th percentile so you can calculate the IQR. Okay. All right, so I'll give you a few minutes to work on that. See what it's.
Or like in the middle.
Oh, yes.
Okay. Try, so don't put converse like close as well. There you go.
Oh, yeah.
Okay.
Perfect.
And can you grab your
Yeah, that's fine. If you want to go 10th, great. If you want to go nearest pound, great. That's totally fine, because if you think about it, put in the right 0.25, it's basically saying, like, which end did we look at? Like, so yeah, so this is like the 75th is associated with the top 25%. So if you do 0.25 and pick right, that's the same as 0.75 pick left. Yeah, it's so weird, but
It is strange. I don't know. I'm sure he wears this setting.
all right, guys, what do you think? What's the IQR? About 8 pounds, somewhere around there. Yeah. All you have to do is your inverse norm for both of those percentiles. And it's interesting now with the left and right option, you could do 0.25 left, and that would give you this score over here. And if you left it as 0.25 and did right, it would give you the 75th percentile, okay? Because the 75th percentile is the top 25%. So it's kind of weird to wrap your head around that. And if that's too much on a Tuesday afternoon, that's okay. You can do them separately as well. I would just have to do for the Q1 value, that's what this first one is, I'd have to do the 0.25 and then 77 and 6 sigma. And I got like around 73 pounds for that. And then for my Q3, I didn't have right and left, so I'd have to do 0.75, 77, 6, and I got about 81 pounds. So the IQR, male, lab, weights, is about 8 pounds. Are you guys starting to see it, how we frequently say approximately or about or it's around this? Yeah, there's not a lot of exactness to what we do in here, and that's okay. Anybody questions on doing the inverse norm part? Not too bad. Okay, so that's essentially the end of Unit 2, and now we're going to move on to Unit 3. So turn the page in your notes. Maybe. There we go. All right, so we're moving on to sampling distributions. This isn't that bad. It's just understanding the idea of what a sampling distribution is. And that's what I'm going to end up explaining with some of these pictures here. So we'll get through it a little piece at a time. All right, so first, we're going to kind of look at an example here where we start with a population distribution and then work our way to a sampling distribution. So first we're given heights of students at Madison are normally distributed with a mean of 66 inches and a standard deviation of 4 inches. So you are given this, it's a normal distribution, mu of 66, sigma of 4. Okay? Then I'm asking you to sketch the population and calculate the probability that a randomly selected student, so a single student, is over 6 feet tall, which 6 feet is 72 inches, in case you didn't know that. So we're going to sketch the population first. Not draw straight today. Oh, that's so terrible. Let's try again. Right. So guys, what's going to go right in the center of my distribution? 66, okay. What's one standard deviation above? 70, 2 standard deviations, and 3 standard deviations, and then 1 standard deviation below. Okay, 2, and 3. Okay. All right, so we want to know the probability that a randomly selected student is over 6 feet tall. Now, that didn't fall perfectly on one of our standard deviations, but I can see the general area. 72 is somewhere in here. So I want to know how likely is it that they fall in that little shaded area. Watch. So what do I use on my calculator to figure out that area? Normal CDF. Okay, we're going back to normal CDF. What's the first number I put in? 72. And then it's 72 and above, correct? So I'm going to go 72, infinity or some really large number. And then my mu was 66. Get in the habit of labeling that. And my sigma was 4. And what'd you guys get? Like 0.067? Is that, yeah. So that means there's about, and I'm going to say 6.7%. You could say 7%, that's fine. So 6.7% chance of selecting a medicine student over 6 feet tall. Okay, so that was just a basic population distribution. We have this nice normal distribution. We found the probability of picking one person with a certain characteristic. Okay, that's what we were doing before, nothing too complicated there. See a few people writing, so we'll get that here. And as always, guys, if you can't read something, let me know. Brian, can you get your gun? Okay, so what we're going to do now, instead of just picking one person, we're going to take a sample of 10 students. So we want to know how likely is it that in this sample of 10, the average of that 10-person sample is over 6 feet. Okay, so we're switching up what we're looking for here. We're not just picking one random person. We're picking 10, and then we're averaging those 10 heights. So let me just show you visually kind of what's happening. First, you've got this population that is normally distributed. That's what this top picture is right here. That's a lovely normal distribution. This is not for the heights, like this is not the data we were talking about. They're telling you the mean is 16 and the standard deviation is 5 for this image you've been given, okay? That's what we've done so far. Now what we're talking about doing is picking different samples and averaging those samples. So that's what's happening in step 2 here. They are picking samples of size 5. So do you guys see, like, there were 2 of them in here, 1, 1, 1. Do you see how that's five people sampled? Okay. And then here's another sample, because you have 1, 2, 3, 4, 5 people. They're taking from this whole population all these different samples of 5 and finding the average of each sample. Okay. That is what a sampling distribution is. You then take every single average of your samples that you got, and you get a new distribution. So this is what a sampling distribution looks like. So when I look at it and I compare the original population to this one, to the one in blue, like, it still definitely looks like a normal distribution, but doesn't it look a lot less spread, like much more condensed? That's what you can expect to happen when you do a sampling distribution. it all becomes much more condensed together, okay? And again, that is taking every single possible sample of 5, averaging it and putting it into your new distribution. So back to our height problem here. You know, we have like 2,200 students in the school. Imagine taking every single possible sample of 10 students. This would take you forever. And figuring out the average heights of each sample of 10 and then plotting those in a distribution. You would get something that looks like that. It would be less spread out than the overall population distribution. Okay? All right. It's okay if that just, you're like, I kind of get it, but I'm not sure I get it yet. That's okay. All right, we're going to keep working with it. Let's go. Okay. Turn the page, guys. All right, so your first step, you can see we've got quantitative and categorical. You have to make the decision on the data you're working with. Is it quantitative or is it categorical? Because then that leads you down a different path. For the center, so with quantitative data, just population distribution, you talked about mu. We are now talking about mu of x bar. And I'm going to write it a little bigger because the symbol's really small there. So mu of x bar. That will always equal the mu from your population. But what it is the average of all of those sampling distributions, like all of the separate 10 people samples together. If we're talking categorical data, and I know this symbol especially did not print well, this should say mu of p hat. And that will always equal the proportion from your population. So again, the difference between quantitative and categorical, you've got to get used to those symbols. Now that we've moved on to sampling distributions, you can't just put a mu. Okay, we got to know, are we talking about mu of x bar, mu of p hat, actual mu? Got to start sorting out some of the symbols, okay? Then spread, when we talk about our standard deviation, so the sigma of x bar, again, I'll write it a little bigger for you. That is the sigma from your population divided by the square root of n.
N is the sample size?
It is, yep, good. N is your sample size. So let's say a sample size of 4 versus a sample size of 100. What's the impact going to be on your spread there? As the sample size gets bigger, the spread gets smaller, okay? So think back to these two pictures. That top one, just the distribution, that's essentially a sample size of 1, okay? Here we had a sample size of 5 and it got narrower. If you had a sample size of 50, it would be narrower than that, okay? That sigma is going to get smaller every time the sample size increases. It's a good multiple choice kind of question asking you what happens as your sample size increases. Your spread gets smaller. And then if we're talking categorical data, this is sigma of p hat. I don't know what happened with my symbols, but you have boxes instead of hats. So, and to calculate this one, it is the square root of p times 1 minus p, again, over n. So that sample size matters.
Is this square root over all of it?
It is, yeah, it got kind of small there, didn't it? Yes, thank you. Okay, then the shape of our sampling distribution. One way that we can know it is approximately normally distributed is related to our sample size. So this is called the central limit theorem. And you can abbreviate it CLT. And what this says, if your sample size I'm not going to be able to write it in there nicely, so let me write it over here. Is large enough. And large enough means a sample size greater than or equal to 30. Your sampling distribution will be approximately normally distributed regardless of the original population shape. So you could start out with a population that's like strongly skewed left or right. You know, you've got this big tail. But if you do sampling distributions with a sample size of 30 or more, you end up with a normally distributed shape. Okay, so, but again, that sample size has to be big enough to make that work. So that's a condition we're going to start checking. We'll talk about that here in a minute. And I know this is pretty abstract until we start doing some problems with it, but hang in there with me, okay? All right, let me go back. Okay, I'm going to write some checks that we have to do under quantitative and categorical data. So these are conditions to check. Got a couple of them. When we get to free response problems, you know, with this unit and continuing through the rest of the year, checking your conditions is kind of like free points on the AP exam. Okay, it's going to have to happen on almost every single free response question. Even if you don't really know where you're going in the question, you can go, okay, I can check some conditions and, you know, squeeze that point out of a problem, even if you're not sure where it's going. So for quantitative data, the first check we have is to determine normality. So you're checking normality. Just say, is it normal? And right now there's a couple ways you can do that. You can have your sample size greater than or equal to 30, or the population is normally distributed. The other thing that might happen is the problem might just tell you, you know, hey, this is normally distributed, and then you're okay with that. But you do have to like show, hey, I've checked this condition. The reason that's so important is because we're using this normal CDF and inverse norm. We're assuming, you know, a distribution with this shape. If that's not actually what it looks like, none of those calculations are going to be accurate. Okay, so that's why we have to check. All right, for categorical data, it's a little different. Again, this is checking for normality. So checking to see if it's normal. You have to show that n times p is greater than or equal to 10. And n times 1 minus p is greater than or equal to 10. So again, these are all based on your first decision of is it quantitative or categorical. Okay, let's try one, guys. So again, we're back to the heights of students here. So we've got the population is normally distributed with a mean of 66, standard deviation of 4. How likely is it that a sample of 10, so this is different than our initial problem, this is a sampling distribution problem, that it has an average height over 6 feet, okay? So first, it's always good to just sort of jot down the things that we know. So we know we have a sample size of 10. We know mu is 66. And we know sigma is 4. Okay, that's all stuff that's just given to us. Then over to the side here, we're going to check conditions. Okay, so the first one is it normal? What do you think? Is it normal?
No.
Here, no. Anybody else? I'm seeing some maybe no's. Okay, what does that little n right there mean? That big capital N, not little n. It means it's normal. It means the population is normal, right? That is one of the ways that you can say, hey, I'm checking my condition for normality, and it is normal.
Is it one that checks also?
So if the population is normally distributed, so like if this one's true, where you're drawing from a normally distributed population, sorry. You don't have to also meet the n is greater than or equal to 30. So yeah, good question there. I don't think I emphasized either one of these. So if they tell you the population's normally distributed, you're good. You don't have to worry about sample size or anything, okay? If you don't know that, then yes, you do have to check the sample size. So good question there. So yes, we can say normal because population is normal. So check. The other one we have to check is this a random sample? So is this random? Does it actually say random sample anywhere in the problem? It does not. So what we're going to write next to this, usually you're going to say, yes, it's stated in the problem. It's not stated, but we want to continue with the problem. So we're going to say assumed. Okay, so you're making note that like, hey, they didn't tell me that it was actually random. We're going to assume it is and proceed.
How do you know the population's normal? That's because
In the problem, when they give you that capital N and then 66 and 4, that capital N indicates normal. Yes.
What would be next to parentheses if it wasn't normal?
You wouldn't have really anything. Like, they wouldn't tell you that information. It's really unlikely that you're going to have a problem that it's not normally distributed, or if the population itself isn't, but your sample size is big enough, they'll just give you mu and sigma, but they won't write it in that way. They'll just be like mu equals 10, sigma equals 5, you know, whatever it is, okay? Good questions, guys. Okay, let's draw a picture of what we're talking about, what we're trying to figure out. So we have a lovely normal distribution centered at 66. And we're talking about our sample of 10 having an average height over 6 feet, so that's 72 inches and up. So again, I'm looking for the area of that shaded part. We have a little more work to do than when we just had a sample size of 1, though. Okay. We know mu is 66. What is mu of x bar? What is mu of our sampling distribution? Look up in your notes, guys. It's also 66. Yeah, do you see it right here, guys? Mu of x bar is the same as mu. Okay? So in this case, that is 66. What about sigma of x bar? How are we going to find that? Yeah, it's sigma divided by square root of n. Yes. So you're right. I'm going to write the formula just so we write that down a few more times. So sigma divided by square root of n. So you are right, 4 divided by square root of 10. So what do we get? .3, 1.26, something like that, right? Okay. All right. Now I have what I need to actually do the normal CDF of this sampling distribution. So I can do normal CDF. So I'm still going from 72 to infinity. My mu of x bar is 66. And guys, label it mu of x bar. And then my sigma of x bar is 1.26. Okay? This is why it's important to label what you're doing. Show like, hey, this is a sampling distribution, not just the population distribution. Okay, what do you get? Yeah, go ahead, I. Okay, what does that mean? I'm sure you're not alone with getting that and kind of. Yeah. There's a lot of zeros, right? Like 0.000, whole bunches of zeros. So what do you think that means as far as how likely this is to happen? Pretty much a 0% chance, okay? So approximately 0. So we'll write the conclusion here, and then let's talk about why this one is 0 and we had like a 7% chance before. Like, let's look at why it's so different. So you could say there are approximately 0% of samples with n equal to 10 that have an x bar over 6 feet. Or you could say that have an average over 6 feet. So don't just answer it with 0%. Like, you've got to tell me, you know, the context. What are we talking about here? I'll look it up a little for you. here. There we go. Okay, so let's talk about this. So when we did this initial one with the population, which really was just a sample of size 1, is what we were doing here. If you look at the spread here with your mu of 66 and sigma of 4, a height of 72, like that was more than 1 standard deviation away, but not 2, right? Like it's in the realm of like, yes, this could happen. It's not crazy unlikely. When you think about the sampling distribution where we've changed our sigma because of the sample size, like let's look at it down here. So now we still are centered at 66, but with your sigma being 1.26, think how far out 72 really is. You know, that's a lot of standard deviations away. When you get beyond 3 standard deviations away, there's basically 0% chance that that's happening. Does that make sense? Okay. I mean, look in this room, randomly picking someone who's over 6 feet versus taking 10 of you and averaging your height and seeing if that height's over 6 feet. Do you see how it's much less likely for it to be that big? Okay. So that's what's happening when we do a sampling distribution. Okay. All right, guys, can I get masks up over noses again? Thanks, Brian. Thanks. Guys, again, I ask all the time because if there's a positive case in here, I have to tell them who didn't wear their mask the whole time. And then you have to go through this whole process of getting cleared. So I don't want to have to do that. All right, any questions on this first sampling distribution problem? Okay, let's turn the page. All right, so we've got, I think this was supposed to be the 2000 census, not the 200 census. It would be an odd census to look at. 2000 census. 80% of U.S. citizens have earned a high school diploma, and we're going to take a sample of 120 U.S. citizens. Okay, do you think this is quantitative or categorical? Categorical. It's either you earned the high school diploma or you did not. Okay, that's not a quantity. That's categorical. Okay, so we're talking categorical. That's your first thought. Which means we're talking proportions like you're going to be dealing with the p-hat. Okay? So you're thinking about the formulas that have p-hat. We need to define what P is when we're doing one of these proportion problems. So let's just up at the top here squeeze in what P is. This is the proportion of U.S. citizens with a high school diploma. And I should probably say according to the 2000 census, but we'll just stop there. And then you can write, P equals 0.8 as part of that as well. Okay, so now we have to find the mean and standard deviation of our sampling distribution for p-hat. Okay, we've got this sample of 120, so it's definitely a sampling distribution. You can make a little sketch if you want. What do you think the center of this distribution is going to be? What's sort of the only thing we know? as far as proportions go? What do you think, guys? What was P equal to? 0.8. That's the center of your distribution. 0.8. Okay, our formulas from the last slide, remember mu of p hat, what did that equal? You can look back if you need to. It equals p, yeah, which in this case is 0.8. And then what about sigma of p hat? What's the formula for that? Perfect. P1 minus P all over N. So we're going to have square root of 0.8. You can write 1 minus 0.8, or I think you could probably handle just writing 0.2. And then your sample size was 1 to 20. What do we get? Go ahead, 0.0, what'd you say? 0.04, yeah, I have 0.0365 written down, but, you know, you don't have to be, there's no rule on, like, it must be 3 decimal places. It's different than calculus here. So try to get those formulas for mu of x bar, mu of p hat, sigma of x bar, sigma of p hat. You've got to know those. Those have to be ingrained in your head, okay? All right, then it's saying, what is the shape of the sampling distribution? Is it normal, and how do you know? Okay, so what was our check, like our condition check for normality with proportions? Go ahead. Good. So we have to check that. So we have to show n times p. So that'd be 120 times 0.8. What do we get?
96.
96. I'd say that's bigger than 10, right? So 96 greater than or equal to 10. And then n times 1 minus p. So 120 times 0.2. What do we get there? 24, also greater than or equal to 10. So you could say the shape of the sampling distribution is approximately normal. And the how do you know is the work you just showed, okay? Okay, I want you guys to try part C. So our sample size changed from 120 to 30. We have to figure out the center, shape, and spread of our sampling distribution. Are any of those going to change? Are none of them going to change? What's going to happen? So I want you guys to try to figure that out, the center, shape, or spread. So I'll give you a minute to work on that. You can work together on figuring that out, but think about center, shape, and spread. Yeah, go ahead. This.
So what I was gonna, here's this and
It's normal, right? You can't make too far off.
yeah.
Or maybe it
Exactly what it is.
actually no, it's 30. So, it's 30. Six.
Yeah, and then I guess it would take the normal salary
Oh, we can check this. Yes.
No, you can say that's no longer. Oh, yeah, you're checking.
No, it actually wouldn't. 6 is less than 30. Okay, so write this here. It's called.
Yeah, yeah, I have that.
So it tells us that 0.8 at high school.
Oh, wow. Oh, I see. Oh, I was just
Oh, yeah.
because I was thinking I was like, sorry, I was right, like, everything.
So fine, the center, have you got
Yes.
So it's like close to the latest one, but it has to be
that would change.
Yes. I like the way that you break
Out. You want to make sure like the wording is. Got it.
that I got it right now.
Oh, okay.
So in the opposite, it's just directly not.
What about
Yeah, smaller. Yeah. That's good. Nice.
Oh, you can play the package,
I know. I know.
Because if it's the sample size is bigger than some samples are smaller, but it's just like.
Give you another minute here and then we'll go through it together.
It's so counterintuitive in my head.
Sample yeah.
Is by saying like the spread gets larger, it's just saying it's more flat, thicker.
Kind of. It's just gonna like cover more area too. Like it's gonna be, the edges of your graph are gonna be like wider.
But like I don't get that because if you have less data, how is it gonna get wider?
You don't necessarily have less data, just so with a sampling distribution, like we're saying a sample size of 30, that doesn't mean just one sample of 30. You have this huge population. You're taking every possible sample of 30. So it's not just one.
Oh, okay.
Yeah? Okay.
So like
It's like a weird.
If you have 100 students, you would take the sample of every different question of 30 students.
Yes.
Okay, that makes sense.
And the average of each of those 30 samples of 30.
Oh, and so since there would be more samples you have, Oh no,
Yeah.
Yeah?
I think I'm overthinking it.
So like we'll go back to the heights just within this classroom. There's like 30 kids. So groups of 10. That's still a whole lot of different combinations of 10 people, right? So I take 10 of you and I find the average of that group of 10. That's like one little thing I'm plotting on my sampling distribution. Like it's 5'8". Okay, I plot that. I take my next little group of 10. I average it. That's my next point on my, like if I was making a dot plot out of it, you know? So it's not less things, it's just smaller groups that you're looking at.
So you have more combinations.
Yeah, that doesn't usually matter because usually the population itself is so big. Like think of, 2,200 students here. Samples of 10 or samples of 5, like the number of combinations is still huge with both of them, so that's not really, it's just the variability within like a group of 10 versus your sample of 30 is different. Like if I averaged a sample of 10, start with just one. Like if I randomly select one student, it could be anything from whatever the shortest person is in here to the tallest person. But if I take 10 of you and average that, like it can't be, 6'5", and it can't be 5'2", because the average just isn't going to be that extreme. If I took all 30 of you and averaged it, that's even going to be a narrower. Does that help?
Yeah.
Okay. It's a hard concept. No. I'm glad you're asking. It just takes time for this to okay, what are we talking about here? Yeah.
I am very confused how we get like the jump from, because I get that it's like 80%.
Okay.
I don't know like specifically what that actually means. Or, like,
So the 80%, like what's that key, the proportion is kind of like it's like a weird thing because this feels more like a quantitative picture.
right.
Yeah, so that's what I think.
It's because we're trying to make a quantitative picture of categorical data.
Kind of. We are finding an average.
So basically, it's just saying the average is yes, they have it.
Is 80%. Yeah.
Okay.
So you're looking at the yeses and the nos, 80%. You're using that as.
Okay.
It's hard. It gets better. I promise.
I'm gonna say it'll sink.
It will. I promise. Hang in there.
The only thing that you notice now is that you had to notice the only
3%?
It's like a matter of a reason.
Yeah, I have 3.7. Oh no, this one. Wait, what are you? So that's 0.3%. Yeah. Yes, that's right. Yeah.
Oh, I have to work here.
It should be. There you go. Oh, Oh, we don't use the 0.9, we use the key, which is 0.8. And then the 0.9, so this is still centered at 0.8, we're saying how likely is this to be 0.8. Okay guys, let's look. Go ahead. All right guys, so part C here. Your sample of 30 versus 120. The mu, the center, that's not going to change. Okay, the mu of p hat is still p, which is still 0.8. Okay, so for the center, no change. Okay, everybody okay with that? The sample size didn't change where your center was. Let's do spread next. I know that's not the order they were in. So if I go through the formula here, sigma p hat, I'd have 0.8 times 0.2 over 30, and I'd get 0.073. Is that different than what I had up here when my sample size was 120? Yeah, it's different, right? So as the sample gets bigger, the spread gets smaller, and reverse is true. If your sample gets smaller, the spread gets bigger. Okay, they are inverse there. So changed. Yes, change. Okay. The shape. What do you guys think? What about the shape? Is it going to change or not? Yeah, over here. What do you guys think?
Because when you check 30 times 0.2 equals 6, which is less than 10, the shape is no longer normally distributed, so it can't.
Exactly. Yeah, when you do your check, that 30 times 0.2, ooh, not greater than or equal to 10. So you don't necessarily know what the shape looks like, but you know it is no longer normally distributed, okay? All right. So sample size will definitely impact the spread and potentially could impact the shape, depending on what the change in sample size is. We're doing okay? All right. Let's try D. All right, D, what is the probability that, we're back to our sample of 120 U.S. citizens, that over 90% have a diploma? Okay? Sketch what we're talking about first. So we sketch our picture. Where is the center of this proportion that we're talking about? Where is P, capital P? What? No, which is an easy thing to think. P has not changed from up here. P's like the truth. The census told us it was this. What was P? 0.8. Yes, that's where your distribution is centered then. We want to know how likely is it that over 90% have a diploma. So we want to know how likely is it that 90% and up have a diploma. If we were just starting with this problem, we'd want to go ahead and go through our conditions check. We'd check for normality and is it random or not. We already did the normality check, so we're not going to write that out again. We're just going to keep going with the problem, okay? So let's write what we know. We know mu of p hat is 0.8, okay? Remember, that is the same as p, that's where it's centered. Sigma of p hat, we figured that out up above. What was it? When we had a sample of 120, what was our sigma of p hat? Yeah, 0.036. Again, I have 0.0365. It doesn't matter. What are we going to use on our calculator to figure out that little shaded area?
CDF.
Yes, normal CDF. Good job. Normal CDF. And what am I going to put in? What do you think the first number I'm going to put in is? 0.9. Now, your next number, normally we would say to infinity, right? You'll still, I think it'll still work for you if you put that in. But since this is a proportion, what's the highest it can go? 1, right? Like, so you could just say to 1. And then mu of p hat, so 0.8, and label it for me, mu of p hat. And then sigma of p hat, the 0.0365. Again, label it. Get in the habit of labeling all those little calculator things for me. And what
system. I like entered all the information and stuff, but it went into like why was
Not really what you want to do.
graph it. Yeah, you probably just thought it was a That's the way. Thank you for walking.
All right, what are we getting? 0.31%. Yeah, something like 0.003 is your answer, which is 0.3%. Yeah. So squeeze that in there, 0.003. So again, we don't just say 0.3%. Like you have to put the context of your problem back in there. So we're going to say there is about a 0.3% chance that a sample of 120 U.S. citizens will have 90% or more with a diploma. Questions on that one? Okay, let's try E, and this will be the last one we'll do today, okay? So our sample size changed. And you have to think about what this means. Like in the last one, I told you over 90% have a diploma. I'm not giving you the percentage here. You guys think about what this percentage would be. Less than 150 out of 200 have it. What is that percentage? Yeah, so I'll start you here. Got this. It's still centered at 0.8. Your p hat, this 150 out of 200, that's 0.75. So we're now looking for this part of it, okay? So go through the same process we just did. Think about mu of p hat. Your sigma of p hat is going to change because your sample size changed to 200. So I want you guys to try that one. Of course, you can chat with each other.
Yes, but it must be 0.
If you forget that and you're like, I don't know what it should be, if you use like negative 9999, you're gonna get the same answer. So if that's throwing you off at all, like thinking about that, you can still use like negative infinity and infinity, and you'll get it right. Yeah, go ahead. You are. That's what I'm doing in a minute. Guys, if you're struggling at all with like, what should the left side be if you're struggling to think back and forth, if you put like negative infinity in on this, you're still going to get the right answer, okay? So if that's like messing with your brain at all, so you could do either of those and you're going to get the right thing. Up to our 0.75. U of p hat. 0.028. Did you guys get 0.028 as your sigma p hat? Okay, okay, good. And did you get something like 0.037?
No. Wait, I did not get ID.
I got that.
Same.
You got that? Okay. Oh, Patrick Moore was trying to give you some nuts there.
Nice.
She's just like. So we could say there is about a 3.7% chance that a sample of 200 U.S. citizens, and yeah, we'll figure out what went wrong, guys, in a second. Oh, we'll have less than 150 people with a diploma, okay? Yeah.
So for my sigma here, I roughed it to 0.03. So then my final answer was 0.0447. Would that like?
As long as I can see that that's like what you used. So as long as you're writing like I used sigma p hat 0.03, like
Yeah, I
it's
wrote
fine.
that in my like parentheses.
Yep.
Okay.
You're
So
good.
then it would be like that would still be correct on
Yes.
this
I know it's crazy, but yeah.
is.
Okay, guys, we'll stop notes there. I'm gonna pass back your test.